let's take a look at another example solving a linear inequality. This inequality that we have, if we try to graph the original equation, so 2x minus 3y equals 9, this is more difficult to get in standard slope-intercept form. So instead, I'm going to graph this by finding the y-intercepts and the x-intercept individually, and then I'll just connect the dots. This is a method that's going to be helpful later on, so I'm going to start doing this now regularly. To graph this equation, this line, I'm going to first see what is the y value if x is equal to 0. So we would get 2 times 0 minus 3y equals 9. And so this simplifies to negative 3y equals 9, and so y equals negative 3. So this gives me 1 point on my line. I have a point at 0, negative 3. Now I'm going to do the same thing, but this time I'm going to solve when y is equal to 0, and I'm going to see what the x value is. So we would have 2x minus 3 times 0 equals 9. So 2x equals 9, and so x would equal 9 halves, which is about 4.5. So now we have a second point at 9 halves, here we go, at 9 halves, 0. And so now I can sketch the line just by connecting these 2 points together. So let's see, we've got our xy plane, we have 1 point at 0, negative 3, so 0, negative 3 would be down here, and we have another point at 9 halves, 0, so that might be about over here. So 9 halves, 0. So we have 9 halves and 0, and we have 0 and negative 3. Now when we connect these points together, we are going to use a solid line because the inequality is greater than or equal to. So we'll connect these with a solid line. And now we need to decide which side is going to be our solution set. So we'll find a point to test, one that we can guarantee is not on the line. Let's go ahead and test the origin, since we know this function does not go through the origin. So I'm going to test 0, 0, since I know that it's not on my line. And we're testing it in the original inequality. So 2 times 0 minus 3 times 0, is this greater than or equal to 9? So is 0 greater than or equal to 9? And that's not true. So this tells us that our solution set is everything that is on the other side of the line. So that would be this lower part over here. So we'll shade this all in. Our solution set is everything below the diagonal line and up to and including the diagonal line. Okay, so we have graphed the solution of our line right here. Let's see, let's take a look at 2 other ones real quick, just to remind ourselves what these graphs would look like. We'd like to sketch the solution set for x less than or equal to 8. So really we need to know, what does the graph of x equals 8 look like? Well, if we're graphing a function that is x equals a number, then that creates a vertical line at that number, because the x value is held constant and the y value can be any value at all. And so if we want x's to be less than or equal to 8, then that means we would like everything on the left-hand side of this vertical line. So everything on the left would be our solution set. Anything on the right-hand side would have an x value that was higher than positive 8. Similarly, if we look at the inequality y strictly greater than 5, really what we need to know is, what does the graph of y equals 5 look like? And if we're graphing y equals a number, that's a horizontal line at that number. So y equals 5 would be a horizontal line at 5, and we would like y to be strictly greater than 5. So since this is a strict inequality, I can't forget the dotted line, right? Because we have a strict inequality instead of a greater than or equal to or less than or equal to. And so if y is going to be strictly greater than 5, then we would like all the y values above y equals 5. So everything above the line, but not including the line. Okay. So just remember, if you're solving an inequality involving simply x or y, it's going to be just a vertical or a horizontal line, depending which inequality you're working with.